Hello and welcome. In this video, we're going to be taking a look at the notes for AP Physics Unit 4, Work, Energy, and Power. Please remember to pause or rewind the video as needed. Let's begin. Section 6.1, Work and Energy. Fill in the table. The first row, we want to explain gravitational potential energy, kinetic energy, elastic potential energy, and internal energy in our own words. Well, here's how we can describe these energies. Gravitational potential energy, which we will abbreviate GPE, is the energy associated with an object's height above the lowest point, or energy of position. Kinetic energy is the energy associated with motion. Elastic potential energy, otherwise known as spring potential energy, is the energy associated with a stretched or compressed object. It could be a spring, a rubber band, bungee cord, you name it. Internal energy is the energy associated with the structure of an object. It is also connected to the temperature of the object as well. For each of these energies, what must an object have or be doing to have this type of energy? So what must an object have or be doing to have gravitational potential energy? It must have the ability to fall. It must have some height above the lowest point in the problem. What must an object do to have kinetic energy? Must be moving. In order to have elastic potential energy, an object needs to be stretched or compressed. Most of the time, that object will be a spring. And what must an object do to have internal energy? The object must also be moving. So why is this so? Because temperature is associated with the average kinetic energy is associated with the average kinetic energy of the particle. And if you have kinetic energy, you're moving. What does it take to increase gravitational potential energy? Well, to increase gravitational potential energy, to increase this energy, work must be done against gravity to raise it to a higher position. To increase kinetic energy, work must be done to speed up the object. To increase elastic potential energy or spring potential energy, work must be done to increase the stretch or compression of that object. And what work must be done to increase internal energy? Work must be done to get the object moving faster. Notice the connection between internal energy and kinetic energy, related through the concept of temperature. Although we will say internal energy is more of an AP Physics 2 topic, it's relevant to talk about it here at least. What does it take to decrease gravitational potential energy? Well, to decrease this, you need to lower. Work must be done to lower the object. To decrease kinetic energy, work must be done to slow the object. To decrease elastic potential energy, work must be done to lessen the stretch or compression of the object. And finally, what must be done to decrease internal energy? Work must be done to, again, get the object moving slower, very similar to kinetic energy. Last row, what system possesses each type of energy? So what system possesses gravitational potential energy? The object and the Earth possess this energy. What system possesses kinetic energy? Well, that would just be the object. For elastic potential energy, it's going to be the object spring system or stretchy object, whatever it is, rubber band. Again, usually most of the time it is a spring. And what type of system possesses internal energy? Well, whatever the object is. Similar to kinetic energy, the object that's moving is the system. Test your understanding. Using the 4 types of energy above, fill in the blanks below, describe the energy transformation. You can use the experiments in Observational Experiments 6.1 on pages 185 and 186. Experiment number 1. You hold a heavy block just above a piece of chalk, which would be the initial state. Then you release the block. The chalk does not break. Now you lift the block about 30 centimeters above the chalk, the final state. If you release the block from a higher elevated position, the block falls and smashes the chalk. Let's see experiment number 1. So when the person does work to lift the heavy block, the gravitational potential energy of the block Earth system increases. Then the block is dropped and the gravitational potential energy becomes the kinetic energy in the block. Finally, when the block crushes the chalk so that the kinetic energy of the block becomes internal energy in the chalk. Experiment number 2. You push a cart initially at rest until it moves fast about 2/3 of the way across a smooth track. A piece of chalk is taped to the end of the track. The fast-moving cart, no longer being pushed, collides with the piece of chalk and breaks the chalk. Let's take a look at experiment number 2. The person does positive work in order to increase the cart's kinetic energy. When the cart crushes and breaks the chalk, the kinetic energy of the block becomes internal energy in the chalk. Experiment 3. A piece of chalk rests in a hanging sling of a slingshot. Then you pull it back until the slingshot is fully stretched. When released from the stretched sling, the chalk flies across the room, hits the wall, and smashes. Let's take a look at experiment number 3. The person does positive work to stretch the slingshot, giving the sling elastic potential energy. The person releases the sling, causing the sling's elastic potential energy to become kinetic energy for the chalk. When the chalk crashes into the wall and breaks, the kinetic energy of the chalk becomes internal energy of the chalk. Now, experiment 4 does not necessarily have a video, but let me describe it. In experiment 4, we have a heavy box that sits on a thick shag carpet. You pull the box across the carpet to a position several meters from where it started. When you reach the final position, you touch the bottom of the box and the carpet. They feel slightly warmer. In experiment 4, the person does positive work to give the box kinetic energy. The force of friction typo there. The force of friction does negative work in order to turn the kinetic energy of the box into internal energy of the box and carpet. So think of it this way. You might be, the work done by friction is decreasing the mechanical energy, but that decrease in mechanical energy is now an increase in internal energy, and thus an increase in temperature. Thus the carpet and the box feel slightly warmer. The 4 experiments in Table 6.1 illustrate positive work being done. The experiments in Table 6.2 illustrate negative work being done. Fill in these sentences. For a force to do positive work, force and displacement must be going the same way. Positive work causes the system's energy to increase. For a force to do negative work, force and displacement must be going opposite ways. Negative work causes the system's energy to decrease. For a force to do zero work, force and displacement must be perpendicular to each other. Zero work causes the system's no change in energy. State the equation for work done by a force that acts through a distance d. Draw a picture in order to illustrate F, d, and theta. What is the equation for gravitational potential energy that is possessed by an object Earth system? Explain each symbol. U sub g represents the gravitational potential energy, and it's equal to mass times g times height. So U sub g is the gravitational potential energy, and that is in joules. M is the mass, that's measured in kilograms. G is the measure of the gravitational field, or the acceleration due to gravity. Unit for acceleration is meters per second squared. And H is the height, the unit of which is meters. Consider a human body. To what part of the human body is the height measured to? Explain this in terms of a pole vaulter. Height is measured to the center of mass of the human body. This is because the center of mass remains constant no matter what the orientation of the human body is. If you look at the pole vaulter over to the right, I'm going to draw a blue dot to represent the center of mass of the pole vaulter. Right here, 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 and right here. So what we can see is it's the center of mass that has to get over the bar, not necessarily arms and legs. Yes, you have to work arms and legs over the bar, but it's the center of mass that really has to get over the bar. What is the equation for kinetic energy that an object can possess? Well, kinetic energy is 1/2 mv squared. K is the kinetic energy, or the energy in motion. M is the mass, again measured in kilograms. And V is the speed or velocity measured in meters per second. Work done by a varying force is found by taking the graph of the force in the situation of the distance that the force pushes the object. Use this fact to answer the following example. The equation is work is equal to force times the displacement, or distance I guess would be fine, times the cosine of the angle. Now, where's this equation coming from? And then let's take a look at 3 different situations. So over to the side here, let's take a look at what's going on. If you have an object of mass m, and you're pulling it at any possible angle relative to the horizontal, this component being f cosine theta, and you're pulling it a distance d, well, work is equal to a parallel component of force times distance. That stands for parallel component. Well, there's the parallel component to displacement right there. So f cosine theta times distance. Now, if you just reshuffle everything and just kind of move the distance out in front, we get work is equal to force times distance times the cosine of the angle. Now, if theta is 0 degrees, meaning the applied force and the displacement go exactly the same way, you have what is called a parallel force. Okay, and the angle is 0. So if we looked at work is equal to force times distance times the cosine of 0, well, the cosine of 0 is 1. So what we get is we get work is equal to a positive force times distance. We get positive work. If theta is 180 degrees, meaning the force is going opposite to the displacement, then work is equal to force times distance times the cosine of 180 degrees. And the cosine of 180 degrees is negative 1, which means we get negative force times distance, negative work. So we have positive work when force and distance go the same way. We have negative work when force goes opposite displacement. Lastly, if theta is 90 degrees, meaning the force is perpendicular to displacement, well, work is equal to force times distance times the cosine of 90 degrees between them, and the cosine of 90 is 0. No work is done. Section 6.2, energy is a conserved quantity. Remind yourself what work does. Work on a system changes the energy of that system. Positive work increases the energy, negative work decreases the energy. How do we find total energy in a system? Total energy is the sum of each of the energies. Okay, so total energy is a capital E, and we would write this total energy as K plus UG, that's gravitational potential energy, plus U sub S, that's spring potential energy, plus U int, which is internal energy. Now, the total mechanical energy is usually just going to be the sum of those 3 right there. And if no spring is in the problem, then it's just going to be the sum of those 2 right there. Explain what a conserved quantity is. Conserved quantity is one in which the total amount remains constant. Can the total energy of a system be changed? If so, how? If not, why? Total energy can change if work is done by a non-conservative, that means external force, like friction, like an applied force. If work is done by some external force, then the total energy can be changed, increased or decreased. We'll talk more about what conservative and non-conservative forces are shortly, so don't worry so much about that definition just yet. It's good to note it right now so that we can see its context, but we'll explain it shortly. State the generalized work energy principle in a short equation and a long equation. All right, well, I'm going to show you the way the book represents this, the ebook represents this, and most textbooks represent it this way. The short version of the work energy principle is simply that the initial energy, whatever that is, plus the work done, plus any work done by an external force is equal to the final energy. Now, the much longer version of that, this kind of breaks down into a lot. And I think it would be better, I know that the textbook writes it like this, it'd be better to write it as the total energy plus the work is equal to the final energy. What this basically means is if work is done by an external force, then you're going to have less mechanical energy than you started. The longer version of this would be K initial, take all of this right here, K initial plus gravitational potential energy plus spring potential energy plus the work is equal to E final, which is K final plus UG final plus US final. That's a long way to write it. I tend to think that there's an easier way to write the work energy principle. And that is work is equal to a change in energy. What that basically means is work can be equal, the work done by an external force can cause something to speed up, meaning change in kinetic energy. The work done by an applied force to lift something can increase or decrease the gravitational potential energy. And the work done to stretch or compress a spring by an applied force would increase or decrease the spring potential energy. Explain why a perpetual motion machine is impossible. Well, a perpetual motion machine is one in which, once it's started, it will keep doing work and transferring energy to the environment forever without any additional input of energy. It's something that just keeps on going with no more fuel, basically. Well, that's not the way engines work. Engines need fuel, and that fuel actually is heat. Heat from various sources is what propels engines to do their job. This does not seem possible because negative work is going to be done over time. Why? Because engines have moving parts. Machines have moving parts, which means there's going to be some internal friction. And internal friction results in a loss in mechanical energy. Bowling ball to face demonstration. Read along with me, please. A student stands against a wall and in front of a bowling ball attached to a rope. The other end of the rope is attached to the ceiling. The ball barely misses striking the ground at point B as you look at the diagram over to the right. Even though friction does act in this situation in real life, let's assume it does not in this scenario. Case 1. The bowling ball is released from point A, which is right in front of the student's nose, where it actually touches the student's nose. The ball swings all the way across to point C and then back to point A. The ball does this. It swings all the way over here and then all the way back. The ball is one gigantic pendulum. Let's take a look at the bar charts that are associated with the various energies. Okay, now if we start this, and I'm going to color code this, I'm going to use two different colors, blue and gray, to represent my energies. The energies would be, of course, kinetic energy and potential energy. Gravitational potential energy, that is. So let's kind of work out the scenario of what's going on. At point A, we have gravitational potential energy, but kinetic energy is 0 because you're releasing it from rest. At point B, all of the kinetic potential energy has converted itself into kinetic energy. The potential energy is now 0 because we're at the lowest point at point B. As the ball swings upward from B to C, we lose speed but gain height, which means we have gravitational potential energy again, but no kinetic energy. And then, of course, the reverse is true, right? The same is true for the reverse pathway. Let's plot this as a bar chart. I'm going to use blue for kinetic energy and gray for potential energy. So I'm starting with a certain amount of potential energy. So I'm going to fill out U sub G for, and I'm just giving it an arbitrary height on the bar chart for now, because I wasn't told exactly what to scale it to. So this is, again, a sketch, not a graph. Now, no work is done as the ball goes from A to B, because we're talking about the ball-Earth system. Therefore, the gravitational potential energy at point A will convert itself to the kinetic energy in point B by the same amount. This kinetic energy will decrease over time and will again convert itself back into potential energy, gravitational potential energy, at point C. The ball stops momentarily, kinetic energy equals 0 at point C, and then starts to accelerate and gain maximum speed at point B again, therefore maximum kinetic energy at point B. And that kinetic energy will again transform itself back into gravitational potential energy at point A. So we go back and forth transferring between the energies. In each force displacement diagram, so an FX diagram is called a force displacement diagram, draw the direction of the force and the displacement as the ball travels from A to B. Now, from A to B, the displacement is in that direction, but the weight is going straight down. So the weight is drawn straight down. The displacement from A to B is down in that direction right there. And theta is an acute angle less than 90. Well, the weight force does positive work on the ball. Okay, and why is that? Because the weight is doing work to increase the kinetic energy of the ball. So let's take a look at what's happening here. The weight force transfers gravitational potential energy of the ball-Earth system to the kinetic energy of the ball. In the next one, we have the tension force. Well, the displacement is still downward this way, but the tension force is along the string, along the rope. And theta would be 90 degrees. Look back at the picture. If we looked at the ball anywhere in this part of the swing, down from A to B, you have the displacement down in this direction, and you have the tension going up the rope. The tension force does 0 work. Tension force transfers no energy to the ball. This is because there is no work done by tension. And tension and displacement are perpendicular to each other. As the ball travels from B to C, now the displacement is up in this direction. And the weight is still down. Theta is now an obtuse angle rather than an acute angle. If we look back at the picture, if we're on our way up this way, the displacement is this way, the weight is down that way. The weight, in this case, does negative work on the ball. Why? Because what is the weight doing as the ball swings upward from B to C? It's slowing it down. It's reducing its kinetic energy. In other words, doing negative work. The tension is still along the rope. The displacement is still perpendicular to tension. So again, the tension force does zero work. Let's take a look over on the side. The weight force transfers kinetic energy of the ball to the gravitational potential energy of the ball-earth system. The tension transfers zero energy to the ball because no work is being done by tension. This is again because tension and displacement are perpendicular. Case 2. Like in case 1, the teacher applies a force to the ball as it travels from B to C. So in other words, the teacher applies a force when the ball is swinging downward from point C to the lowest point B. The force applied is directly to the left, meaning when the ball is right here, a force is applied in that direction there. Well, what's going to happen there? Well, from A to B to C, everything is going to be exactly the same way it was in the previous problem. So we start with gravitational potential energy. This converts to kinetic energy at the lowest point, which is point B. This converts back to gravitational potential energy. At point C. Now, when the ball is swinging from point B to point C, work is done. Now, what is work doing? Work, if you follow the picture here, the displacement of the ball is this way. Draw that a little bit smaller. And the angle between force and displacement is obtuse. If we go back and revisit that, when the angle between force and displacement is obtuse, meaning greater than 90 degrees, negative work is done. When the angle between force and displacement is acute, meaning less than 90 degrees, positive work is done. And when the angle between force and displacement is 90 degrees, zero work is done. So that is clearly showing you an obtuse angle between force and displacement. And if you really thought about it, a force applied to the left is slowing down the ball, meaning negative work is done. So I'm going to give an arbitrary amount of negative work at this point right here. And if I had 7 units of gravitational potential energy and the work done is 2 units, that means my kinetic energy at the lowest point is now down to 5 units because this has subtracted from this to get this. And if no work is done, then that means these 5 units of kinetic energy convert themselves into 5 units of gravitational potential energy. For each force displacement diagram, draw the direction of the force and the displacement of the ball as it travels from C to B. Please note that the numbers are made up for the sake of the argument. Now, from C to B, the displacement is down in this direction, and the force, well, actually, no, I'm sorry, we should be looking at the weight. So the weight goes straight down. There's an acute angle between them, which means the force, the weight, is going to be doing positive work to accelerate the ball. The weight force transfers 900 joules of gravitational potential energy to the Earth ball system, or ball-Earth system, however you want to state it, and this turns into 900 joules of kinetic energy of the ball. Well, again, we've got the displacement going down in this direction. You've got the tension going up perpendicular to it, and perpendicular forces do zero work. The tension force transfers no energy. The applied force, directed to the left, is an obtuse angle measured with the displacement. Therefore, the applied force of 300 joules does negative work on the ball. The applied force does 300 joules of negative work, to reduce the kinetic energy to 600 joules. Explain how you knew the sign of the work done by the weight force. The sign is positive, work is positive when the angle between force and displacement is acute, or less than 90. We know the tension force is doing zero work because tension is perpendicular to displacement. And we know the applied force does negative work because the angle between the applied force and the displacement is obtuse, or greater than 90 degrees. Roller coaster example. A roller coaster car carrying a single child has a total mass of 100 kilograms. It is moving very slowly at point A, the top of the first hill of the track. The net force acting on the car parallel to the track is represented by F parallel. That's what the lines mean right there, parallel force. The strength of this force is shown in the graph as a function of distance along the track, where, quote, forward net force is positive. The only individual forces acting on the car are the weight and the normal force, not the force of friction. Note that various points along the track are labeled B through E. Part A, determine the net work done on the roller coaster between the positions 0 and 100 meters. Well, this can be found the net work is the area under a force distance graph. Now, specifically, we're going to take the area from this point right here. We're looking obviously at a triangular region. So the area of that would be 1/2, the base is 100, times the height, which looks to be 400. In which case we get 50 times 400, which is 20,000. 20,000 joules Part B, is the net work found in Part A due to the normal force, the weight, or both forces do some work? Since the normal force acts perpendicular to the displacement of the roller coaster, then the normal force does no work during the ride. The net work in Part A is due to a component of the weight moving parallel to the track. In other words, ladies and gentlemen, if you remember work with inclined planes, and you have components of the weight, the component that is mg sine theta that points downhill, that is the parallel component of force that's actually doing work. Part C, does the car move uphill or downhill as it travels from point 0 to 100? What is the change in height for the car? Explain your reasonings. Well, the car is exclusively moving downhill from 0 to 100 meters. The change is 20 meters, and I'm going to show you how to figure that out. This can be found by the fact that the net work done by gravity on the roller coaster is equal to the gravitational potential energy the roller coaster had before going downhill, meaning the net work is also equal to a change in energy. Well, the net work that is done on the roller coaster is equal to the potential energy it had before it went downhill. And we'll use that with mgh, and we'll simply solve for h. So h is the gravitational potential energy divided by mg, which would be the 20 joules of work, 20,000 joules of work, excuse me, divided by 100 kilogram mass times 10, and you're knocking off what, 3 zeros? There you go, 20 meters. Part D. Does the car move uphill or downhill as it travels from 100 to 200 meters? Well, let's see what's going on. From 100 to 200 meters, the area is negative. Now, if the area is negative, that means there is negative work done on the car. Negative work done usually would indicate, or not usually, always indicates that there's a loss or a decrease in mechanical energy. Negative work, we have to be going uphill because the parallel force of gravity is now slowing down the car rather than speeding it up. Okay, now let me redraw this right here so that it makes more sense. What we have here is we have a roller coaster car that is starting at the highest point of 20 meters. That's the gravitational potential energy, that's the height, excuse me, due to the maximum gravitational potential energy. We know that the net work done by gravity between points A and C, point A and C would be the upper triangular region. That would basically be the work done by mg sine theta as the car is racing downhill. And then from C to E, the car is coming back uphill, but it's not coming back up all the way. Okay, and how do we know this? Well, we can figure that part out too. If you look at the area of that, the area of that has the same base but half the height. So same base but half the height means it's half this area right here, the work from 100 to 200, that region right there, is negative 10,000 joules. Okay, now the negative just tells you there's a loss in energy, right? And so negative 10,000 joules corresponds to half the height. So instead of 20 meters, it would be 10 meters. So that's how this picture of the actual roller coaster can be drawn. Part F, create energy bar charts for each point that the roller coaster passes through. Well, we're starting this, and I'm going to use blue and gray, blue for kinetic energy, gray for gravitational potential energy. Well, I'm starting this journey at point A with 20,000 joules of potential energy. At point B on this point is halfway between point C and A. It's half the distance traveled, but it's also half of the energy too. It's half of the triangular region. So point B is the halfway point on the curve right here. And that would be a point where we have half the potential energy has decreased by half, and the kinetic energy has essentially equals that same amount. The total must equal 20,000 joules for total mechanical energy to be conserved. At point C, we have nothing but kinetic energy all the way down. Okay, so at point C, the potential energy, the gravitational potential energy at point A is completely transformed into kinetic energy at point C. Now point D is half the height of point B. So if point D is half the height of point B, that means point D has half the potential energy of point B. Half the potential energy, half the height. Now, if it has half the potential energy, that means you have to have 3/4 of the maximum kinetic energy to add up to 20,000 joules. Remember, the total energy needs to add up to 20,000 joules. Therefore, the kinetic energy at point D should be 15,000 joules. And then lastly, since point E is at the same elevation as point B, you would expect the exact same energies as point B. Section 6.4, Quantifying elastic potential energy. What is the equation for force that exerts a spring on an object that compresses or expands the spring? Well, this is known as Hooke's law. Which tells you the restoring force is proportional to the negative of the displacement of that spring. Okay, now I'm just going to write it as F, not necessarily restoring force, but F is equal to negative Kx. Negative because the restoring force is always going opposite to the way you displace. So F is the restoring force exerted by the spring in newtons. K is the spring constant. In newtons per meter. And X is the stretch or compress distance of the spring. And that's going to be in meters. Explain the negative that you put in the equation above. Well, again, the negative sign refers to the fact that the spring falls back on the object. The spring forces back. It pushes or pulls back on the object in the opposite direction to displacement. What is the symbol, what is the equation, for the stored energy in a spring and when the spring is compressed or expanded? Well, the equation would be U sub S, that's the spring or elastic potential energy, and that's equal to 1/2 times K times X squared, where U sub S is the spring potential energy in joules, K is the spring constant, in newtons per meter, X is the stretch compressed distance. In meters. Okay. Test your understanding. The graph shown on the right represents the force applied by a spring as a function of the stretch. 5 data points were taken and plotted on the diagram. Draw a best fit line to the data and answer the following 2 questions. Now let's draw a best fit line first. Okay. Now, what is the spring constant of a spring? Well, we're looking at a force stretch graph, and if we use the equation F equals Kx, this is a variable, and K is a constant, spring constant. And so if I rewrite this, F over X equals K. The spring force is my rise. The stretch distance is my run. And rise over run is slope. So since F over X equals K, that means the slope is K. So let's figure this out. Zoom in on the graph. I mean, that looks pretty linear all the way up. I'm going to say it's more or less up 50 over 0.1 pretty much just every time. So K be about 50 newtons over 0.1 meters, which was about 500 newtons per meter. So we can find K by finding the slope of a spring force distance graph. How much work is done? Well, work is the area under a force distance graph. Okay, to stretch it from 0.3 to 0.5. So what we want to do is we want to focus on just this region here from 0.3 to 0.5. You guys can all see that trapezoidal region right there, which really kind of breaks down into a triangle right there, and the the triangle above and the rectangle below. So the triangular region, right, has a base of 0.2 and a height of 150. That would be 30. And then the triangle has a base of 0.2, a height of, let's see, what is that? From 100. So half of that would be 50, which would be 2. So the work, right, is going to be the 30 joules plus the 2 joules, or 32 joules. So with this particular question, we're getting good practice at knowing what the slope gives us and what the area gives us. Section 6.5, friction and energy conversion. Write an equation for the work done by friction on an object. Explain why friction always does negative work on an object, then write the equation for the increase in internal energy for a system where friction acts. Well, let's take a look at the second part of this, where we're explaining why friction does negative work. Well, friction always does negative work because friction opposes displacement. Another way you could think about this is that friction, especially sliding friction for that matter, always results in an object slowing down. And if an object is slowing down, it's reducing kinetic energy. So if the kinetic energy is decreasing, mechanical energy is decreasing, that's because negative work is done by friction. The equation would look like this. The work done by friction is equal to, well, work, let's just put this in general. Work is equal to force times distance times the cosine of theta. Well, the work done by friction would be friction times distance times the cosine of 180 degrees. Now, the cosine of 180 degrees is -1, which would be telling us that the work done by friction is equal to negative friction times distance. Now, how else could we write this to show an increase in internal energy? Well, work is also a change in energy. So we could write this to show that the friction, the loss in mechanical energy of friction, the loss in energy is the increase in internal energy. And so we would say that the work that contributed to the loss of mechanical energy by friction is contributing to an increase in mechanical or an increase in thermal energy or internal energy. So we're talking about the internal energy that is made up of the molecules and the motion of the molecules and relates itself to ultimately the temperature of the molecules. And so again, the loss in mechanical energy done by friction results in the increase. Basically, energy coming from somewhere goes to somewhere else. Energy is not lost, it's not created, it's not destroyed, it's just changing forms. So if it is lost from one form, it's gained by another form. Another way we could state this would be the work done by the internal energy, or I should say the change in internal energy, is equal to a positive friction times distance. It's the positive version. So the negative, the energy lost right here is the energy gained here. Conservative and non-conservative forces. Now, this is a section that's not in the e-textbook, so let's take a second to go over what is a conservative force and a non-conservative force. Well, conservative forces are forces for which the following are true. Okay, now do keep in mind, if one bullet point is true, then they're all true, okay? But let's take a look. A conservative force is one that has a potential energy associated with it. So that would be what? Gravitational potential energy, spring potential energy. What that tells you is gravity and spring forces, because those are forces that have potential energies associated with them, are conservative. Now, another one that we haven't really had been exposed to would be an electrical force. Electrical forces, we can have electrical potential energy. So electric forces would be conservative forces as well. But we don't really deal so much with electric forces in AP Physics 1. A conservative force can change kinetic energy into potential energy and potential energy into kinetic energy. There's a nice conversion between the two. A conservative force does work, but the amount of work depends on the starting and ending point, not the path taken. Now, a non-conservative force or a dissipative force is one in which you have a change in mechanical energy as a result of that force. So, for instance, they do not have a potential energy associated with them. So that would be things like external forces. What are examples of external forces? External applied force. External tension. Say there's an external rope that's, accelerating an object. Or possibly even friction. These are all things that would change the mechanical energy of something. They change the kinetic energy into heat, sound, or light energy, but not necessarily potential energy. So think about how those would work, how these would work to accomplish this. Right, friction, for example. Okay, what does friction do? Friction, the work done by friction, transfers the kinetic energy of the object into the sound energy and the internal energy of the air molecules that are surrounding the object. Those increase with the decrease in kinetic energy. And also, non-conservative forces, they do work on an object, but the work definitely depends on the path of the object taken. Okay, here's a good example of this. I'm going to show it to you in terms of a conservative force. So let's talk about you drop a block straight down, height h. Okay, that's the first scenario. Then the second scenario is that block drops from the same h, but slides down a frictionless hill. Since the h is the same, that means mgh, potential energy, converts into kinetic energy. In both cases, there's no friction reducing mechanical energy, so mechanical energy is conserved. Conservative forces are one in which mechanical energy is conserved, right? Non-conservative forces involve a loss in mechanical energy somewhere. So an example of that one would be, let's say you had a block going down an incline here where there was friction. Now the potential energy that you have here, it converts into kinetic energy, all right, but there's also a loss in mechanical energy. So we'd say the potential energy plus the work done by friction, that equals the kinetic energy at the bottom. So you're going to have less kinetic energy at the bottom here than you do here because of the non-conservative force of friction reducing that mechanical energy. So we're just giving these forces a new name, conservative or non-conservative forces. So again, let's summarize here. Name two conservative forces. Well, gravity, right, or weight, right? You guys know it as both. And spring force would be two mechanical forces. You could put electrical force in this as well, but let's focus on the mechanical forces since that's the focus of our studies. And non-conservative forces, I mean, friction, and external tension, right, and applied force. Those are all things that are going to kind of increase or decrease mechanical energy. So when conservative forces act, mechanical energy is conserved. When non-conservative forces act, mechanical energy changes. Test your understanding. The graph shows the kinetic and potential energies of an object that travels along a track, during which two intervals, labeled A, B, C, and D, during which two intervals do only conservative forces act on the object. Explain your reasoning. Conservative forces are going to be acting when there is no loss in mechanical energy. Okay, and here's what I mean by that. The total mechanical energy is K plus U. All right, and here's how we can look at this. The original K, let's look at what's going on before we even get to interval A. Before we get to interval A, K is 3 units tall. Whatever units is it, 3 joules. If we want to just make it simple and say each line is 1 joule. 1, 2, 3, 4, 5, 6, 7 joules. So we're looking at 3 units plus 5 units, right? That means the total energy so far right here is 3 plus 5, or 8 units. Okay, now let's look at partway through section A. So if I look at this point right here, and this point right here, which is right above it, I look at that exact moment right there, then we have 2 units of kinetic energy and 6 units of gravitational potential energy. Well, the 6 plus the 2 do add up to 8 units. So we are conserving energy in segment A. Okay, but is that true in the other segments as well? We need to find out. Okay, what's going on in this segment here? Well, in segment B, you have the same kinetic energy, but you do not keep the same, you have a drop in potential energy, a drop in gravitational potential with the same kinetic energy. So that means as the interval B goes along, there is a loss in total mechanical energy here. Okay, and then what's happening in interval C? Interval C, you're raising your kinetic energy from 1 unit to 3 units. Okay, 1 unit here plus 1, 2, 3, 4, 5 units is only 6 units. Okay, so we already lost mechanical energy to that point. So far we have a total mechanical energy of 6 units. What about at the end here? At the end, our total mechanical energy is 3 units plus 1, which is 4 units. So again, we've lost mechanical energy here too. Okay, I hope you guys see that. You're gaining kinetic energy, but you're losing more potential energy than you're gaining. Therefore, there's an overall loss in total mechanical energy. And then if you look in D, you're raising your kinetic energy. Your kinetic energy is 1 unit. Your potential energy, your kinetic energy is 3 units tall. Your potential energy is 1. That's a total of 4 units of E is 4 units. And then over here, kinetic and potential energy are both 2, so E is 4 units as well. So here, the potential energy raises as the kinetic energy falls. Therefore, you are conserving energy in interval D as well. Okay, let's go ahead and summarize. Conservative forces act on the object during interval A and interval D only. This can be seen because the sum total of energies between kinetic and potential always adds up to a constant value. Or you can look at it this way. The increase in one energy is completely balanced exactly by the decrease, the same amount of decrease with the other energy. Section 6.8, power. Explain what power is. Give a general equation with words for power. Well, power, ladies and gentlemen, is the rate at which one energy is converted from one form to another. When we see the word rate involves time. So let's come up with an equation for this. Power is equal to work over time. So power equals work over time. Now, that's not weight, that's work. Okay. Do keep in mind, work could be written as force times distance divided by time. Don't forget, ladies and gentlemen, that distance divided by time is speed. So force times speed is another way. So we have two equations for power. Power is equal to energy divided by time, and energy usually relates to work. Or power is equal to force times velocity, one of the two. Explain what a watt is. A watt is the unit of power, okay? It's 1 joule per second. So the watt, now the symbol for watt is just a capital W. Okay, so for instance, a light bulb is rated at 100 watts. What this means is 100 watts means 100 joules of energy each second. Okay, what the light bulb is doing is the light bulb is converting 100 joules of light energy to heat every single second. That's what the power of a light bulb is. And that's a lot of energy. Therefore, the light bulb is not only hotter, but brighter. More wattage, brighter bulb. This means that 100 joules of electrical energy converts into internal energy, meaning thermal energy, every second. In the next example, an electric motor delivers 500 watts of power. This means the motor converts 500 joules of electrical energy into kinetic energy every second. Lastly, a car motor goes from 0 kinetic energy to 10,000 joules of kinetic energy in 10 seconds. The power delivered by the motor is 1,000 watts. Okay, now how do we get this? Well, the change in kinetic energy is the work. Remember, work is equal to a change in energy, and what's changing is the kinetic energy here. So work is equal to the change in kinetic energy, which is 10,000 joules. Power is the work divided by the time, or the rate at which work is done. So we take our 10,000 joules divided by 10 seconds. You can see one factor of 10 cancels. And we're left with 1,000 joules per second, or 1,000 watts. That's how we came up with that number. Again, this means the motor converts 1,000 joules of thermal energy into kinetic energy every second. Please remember to again pause or rewind the video as you need to do so.